Hello everyone, and welcome to another seminar of Physics Latam. Today we are very happy to have Professor Thomas Creutzig from Friedrich-Alexander-Universität with a talk on logarithmic CFT. Please remember to raise your hand at any point if you have any question, and I will leave you with Thomas. Please go ahead.
Yeah, thank you very much. Yeah, if I don't see your hand, just unmute yourself and then ask a question. Don't hesitate asking a question. Okay, I want to give you an idea what is logarithmic conformal field theory. And maybe at the same time, I want you to give you an idea how one thinks about conformal field theory from a mathematical point of view, or maybe simply from a certain perspective. So when I try to explain to my students what is meant by a conformal field theory, or maybe its mathematical analog, I always say it's the attempt to formalize and at the same time chiralize, meaning quantize in some sense, analysis, harmonic analysis of functions on certain manifolds. And in this spirit, I want to give you my presentation. So, and at the same time, I want to give you an idea of logarithmic conformal field theory. So of course, I don't know exactly what has happened in your course so far, but usually one introduces two-dimensional conformal field theory and then discusses it in good examples. So one very good example is the free boson. Another very good example is the Virasoro algebra. And they are of usually you say rational type. And what I'll do today is I will rediscuss the free boson and then give you another example of a conformal field theory that is not of the rational type, but of the so-called logarithmic type. And hopefully you get an idea what it is. And the free boson, the way I'd like to think about it is you first start with a classical example. And if you're a physicist, you can think about this classical example as, by classical, I mean quantum mechanics. And if you want to think about it from a mathematical point of view, you're studying functions on a certain space. So the easiest example to study is in quantum mechanics is surely a free massless particle without any potential. Then all you want to know is a momentum and position. And you probably know that the momentum operator is given by the derivative up to an I and an H bar, which I will ignore. And the position operator is just the multiplication by the coordinate x. Now, for us, this just means we have a certain differential operator, d dx, and a differential operator naturally acts on functions. And there are then very special functions, namely eigenfunctions for your differential operator of interest, and everybody knows that the eigenfunctions for d dx are just the exponentials. Right? So e to the nx has eigenvalue n, and in quantum mechanics, you would then say the wave function of type e to the nx would have momentum n. And here I simplify notations. In quantum mechanics, you would have a 2 pi I floating around, which is simply ignored here. Then you also would like to associate to this function some kind of energy, which in quantum mechanics you call a Hamiltonian. In that case, it would just be the second derivative, and so saying that the energy is n squared, momentum squared up to normalization. Okay, and now this is the baby example, right? And in general, one maybe would like to think of quantum mechanics as the following data. One has a set of physical quantities, certain differential operators. So here in this case, this would just be the differential operator d dx and x. And these differential operators act naturally on a certain space of wave functions. And that means a certain space of functions that satisfy certain integrability conditions, because as a physicist, you would like to get expectation values which are certain integrals. And now a very good idea is usually organize the space of wave functions in a good way. And that is usually done by organizing it into representations of the underlying symmetry algebra. So for example, in quantum mechanics, if you do angular momentum, you have these operators L plus minus and Lz describing the angular momentum in certain directions, and then organizing functions into representations that transform nicely under these operators is usually a good idea. Okay. So this is maybe just a short recap of quantum mechanics. I do this because one way to think about two-dimensional conformal field theory is to lift classical or quantum mechanics to a field theoretical version. And we are in 2 dimensions, so that means you know that CFT is described by maps from Riemann surfaces into a certain target. And so here, if you want to formalize it, then we think about conformal field theory by lifting all structures somehow to maps from Riemann surfaces to something. So in particular, one wants to not have an algebra of differential operators anymore, but a kind of chiralized version of that. That means differential operators or something analogous to it that depends on the coordinates on your Riemann surfaces. And then one wants to analyze, and this is what one would then call the chiral algebra or the symmetry algebra of the conformal field theory. And then one also, of course, wants to lift the data of interest, that means the wave functions or the functions, to also some functions, some operator valued functions that represent the space of states of the conformal field theory. And I want to walk you through this idea a little bit in the example of the free boson, and then generalize to an example that you surely haven't seen before. Okay, now I'm a mathematician, and I'll present this a little bit from the mathematics sides, but not too much. So the mathematicians have tried to formalize quantum field theory in general in many ways, with maybe not too much success. But one thing that can be formulated rigorously is the symmetry algebra, the chiral algebra of a 2D conformal field theory. And the mathematician calls this a vertex operator algebra. So I will use this name, and you think about it as the symmetry algebra of a conformal field theory. And we see how this now goes. So first of all, the definition is a vector space that has data that one wants, right? And what one wants is one wants to associate to every element of this vector space a field, a quantum field. That means a function that acts on the underlying vector space. This is formalized with these fields are here called y of v and z, so they depend on an element of the space of states, the vector space, and the coordinate. And then it's an infinite sum where each coefficient is an endomorphism. That means an operator that acts on the vector space. And then it has a distinguished vector, the vacuum vector, and also a translation operator. This translation operator is usually identified with the L-1 of the Virasoro algebra. And these have to satisfy a certain axioms, namely the field corresponding to the vacuum is just the identity. And you have to have a state field correspondence, meaning if you act with a field on the vacuum, and then you get a Taylor series, so no negative powers in Z, and the constant term is just your original vector back. And you want to be able to go back from a state to a field and vice versa. And via this relation, you can do this. And then the third one is that the L-1 acts as a derivative. And the most important axiom you know is locality, that two fields quantum commute as long as they are separated in space-time. which is this condition here. So these are the axioms, and it's just for you to have seen this. Okay, now this locality axiom can be rephrased to say that fields obey an operator product algebra. That means you can take the product of two fields, you can expand it in a certain domain, and then it gives you an operator product. So I assume that you have seen these things in your lecture somehow. For example, you surely have seen this in the example of free boson and Virasoro algebra. And mathematical, this is a consequence of this locality axiom. And what I defined in the previous slide is called a vertex algebra, and the name operator. So the naming is not very clever, maybe. Anyway, the name operator refers to that this vertex algebra also has a Virasoro subalgebra. So that which is of course a must in two-dimensional conformal field theory. And Virasoro subalgebra means you have a vector which you call the conformal vector, so that the associated field satisfies the OPE algebra of the Virasoro algebra, right? Which is this expression. And in addition, you also require that the translation operator is the L-1. Okay. Now, this is the definition. And if you were to take a course on vertex algebras, then you would get this definition. Then one would show that this definition implies that you have an operator product algebra. And then you would get, as a first example, the free boson. It's also called the Heisenberg vertex algebra. So what do you do there? So you remember, the idea I want to promote is that you like to lift, you like to chiralize in some sense quantum mechanics. And the free boson simply wants to chiralize quantum mechanics on the real line or the unit circle, if you wish. So that means the symmetry algebra is just given as the one-dimensional Lie algebra, abelian, given by the differential operator ddx. So we want to have a field that corresponds to these differential operators. Well, and if we formalize it, we just don't want to always write ddx, so we just call this Lie algebra, the one-dimensional Lie algebra generated by an element V. And then its affinization is that you now take Laurent polynomials in V and centrally extend. And then, because you don't like a clumsy notation, you write xn for t to the n times V. And the commutation relations are these ones. And these commutation relations you hopefully recognize as the commutation relations of the free boson conformal field theory, better it's chiral algebra. Maybe you didn't have the K because the K is of no importance, and as we will require that it acts by a fixed scalar, and we don't do any harm if we set this fixed scalar to 1. So the idea here is that we have here a one-dimensional Lie algebra that we now call x0. Remember, the identification is xn is equal to t to the nv. So the vector v of our original finite dimensional Lie algebra is identified with x0. And chiralization here simply means that we take the loop algebra of this Lie algebra, meaning we take polynomials in T and T inverse with coefficients in this Lie algebra, and then all we do is this mild central extension. But this is not so mild because we can use this algebra to get a vertex algebra, right? Namely, what do? We start with a vacuum vector and declare to be a vacuum vector in the sense that it is annihilated by all positive modes. So that means we simply require that x to xn acting on the vacuum is always negative if n is positive. And I should have written n greater or equal to 0 for the zero mode, we require the same thing. And then we set the vector space, the space of states, to be the polynomial ring in the negative modes. And then we also call this vector space the Fock module, or the vacuum Fock module of the free boson. Okay. Now, this algebra is generated by a single field, which we call x of z. Maybe in your lecture it had the notation derivative of x. Anyway, I call it like this. It is this infinite sum over the integers xn z to the minus n minus 1. And if you act with this on the vacuum, because the zero mode and the positive modes annihilate the vacuum, the first mode that doesn't annihilate it is x minus 1. And because of this minus n minus 1, it comes exactly with a constant, is exactly constant in z. And then the first subleading term corresponds to x minus 2, etc. So we nicely see in this case the state field correspondence, and at the field x of z corresponds to the vector x minus 1 acting on the vacuum. Now, using the commutation relations of the Heisenberg, of this Lie algebra, the Heisenberg Lie algebra, one can compute that the OPEs of this form the free boson operator product algebra. And now, okay, so the idea is to chiral. You have a quantum mechanical model, as we have here, functions on the real line. So the differential operator is just ddx, which we chiralize to this free boson field x of z with underlying space of states, the vacuum Fock module. Now, the next thing is one wants to chiralize representations. And so the first thing is so that and for that one first has to think about modules, because one always wants to understand how something acts on something. So one wants to do representation theory. And let me here quickly recall the definition of a representation of a Lie algebra. A Lie algebra module is a map that assigns to every element in the Lie algebra a linear map on your underlying vector space, so an element in an endomorphism space. And this map has to respect the Lie algebra structure. So here at the right-hand side, linear maps, if you fix a basis, you can and should think about it as matrices. So that means you have you can take the product of matrices and the commutator of matrices, and being a representation of a Lie algebra means that this map pi respects the commutator in the sense of this formula. Okay, and now for a Lie algebra itself, how is it defined? It is a vector space together with a product, a bilinear product that is denoted by this commutator symbol, such that this product is antisymmetric and obeys Jacobi's identity. Antisymmetry, one can remember, it just means the commutator of A and B is equal to the minus the commutator of B and A. And Jacobi identity is a certain, well, let's say, associativity property of this type, which one can't remember that easily, probably. Now, why am I stating this? Because the notion of a vertex algebra module, really all these things, they come kind of naturally from Lie theory in many respects. The data you want to be very similar. You again want to have fields. And we want to every element in our vertex algebra, we want to have an associated field. But now instead of the field acting on itself, it acts on a different vector space M. So that's the only difference. So the only difference in this definition here of a field for a module is that here we have end M instead of end V. That means operators on the vector space V and M and not V. And now the point is one wants to give this, and now one wants these fields corresponding that act on the modules also to satisfy a certain identity, but now the locality condition is maybe not optimal, and it's kind of more naturally to exactly lift the Jacobi identity of Lie algebras, and the lifting of that it gives an identity that is of this type. Hard to remember the exactly form, but you see what it involves is that products of the fields in different orders, right here, field associated to A times field associated to B. Here we stop the order, and here we convolute, here we associate, and there should be a certain identity satisfied, which is where this delta is a formal delta distribution. So anyway, this is the definition. Not so easy to remember, but maybe one thing one sees is that this identity has some similarity with Jacobi's identity for Lie algebras. This is where it comes from, and it ensures that a certain single valuedness of correlation functions, in fact. Okay, so these are general definitions, and now we want to see how this works in our vertex in our free boson settings. So our idea was we want to build a complete conformal field theory somehow by chiralizing or lifting functions on the real numbers. So the underlying symmetry algebra was just given by the differential operator ddx, one-dimensional abelian Lie algebra, which we lifted to the free boson field. Now next we want to lift modules. So the natural module for the operator ddx is just the eigenfunction e to the nx. This means the function that has eigenvalue n, it generates a one-dimensional vector space. And this is clear because we are looking at representations of a commutative algebra, and the commutative algebra has always the property that any simple module, any irreducible module, is just one-dimensional. So we want to kind of lift them. And the lifts, they are called the Fock modules of weight lambda. This means we proceed with the construction of the module almost exactly in the same way as before, just that we now choose our favorite weight lambda, say a real number or an integer or a complex number, depending on our taste here in the moment. But what we do is we also take just a one-dimensional module for the non-negative modes, where we simply require that all modes xn act as 0, except that the 0 mode acts by multiplication by the scalar lambda. The scalar we like to call a weight. You can also call it an eigenvalue, it's fine. So this means we think about the positive modes as annihilation operators as before, and then the Fock module for the free boson is again just the creation operators, the negative modes, acting freely on this top-level vector. That means the whole space is created by the negative modes. And the field x of z acts on this f or this Fock modules in the obvious way, right? Because the field is just given by this sum xn z to the minus n minus 1, and the modes xn act on f lambda as prescribed here. So this means the functions on the real line, or the eigenfunctions for ddx, they are lifted to Fock modules. Now, but we really want to go to conformal field theory data, and conformal field theory is really described by fields in Z and Z bar, which are quite complicated. And this is now where we slowly will go to next. So what else, what other structure do we have if we look at functions? Okay, the functions are acted upon by this differential operator. And if we have two functions, then we can multiply them, and the product is again a function. Here for our eigenfunctions of the differential operator ddx, this is quite simple, right? Because e to the nx times e to the mx is just e to the n plus m times x. And in particular, we see if we have the eigenfunction of eigenvalue n times the eigenfunction of eigenvalue m, then the product is the eigenfunction of eigenvalue n plus m. And representation theoretically, this just means that you can think about one of the functions, e to the nx, for example, as an intertwining operator. That means an operator that maps the function e to the mx to the function e to the n plus m times x. And the map is very simple, namely just given by multiplication, say from the left. Okay. And intertwining operators, mathematically, they do realize tensor products. That's why they are important. And so here, let me, and here, what looked quite simple on the previous slide is reformulated abstractly. Namely, here we take in general a Lie algebra G and three modules. That means three vector spaces M1, 2, 3, on which the Lie algebra acts via the representation maps pi 1, 2, 3, or pi M1, pi M2, pi M3. Then an intertwining map in general is a linear map from the tensor product of the vector space, first two vector spaces to the third one, that is compatible with the Lie algebra structure. That means it satisfies a Jacobi-like identity, and this Jacobi-like identity is given by this formula. And it's yeah. On the left-hand side, you have a kind of a commutator, right? And here on the right-hand side, you associate in a certain way. And this Jacobi identity is exactly what you need to require in order for this linear map, this intertwining map, to be a map of representations of the Lie algebra for G module map, for the map to respect the Lie algebra structure. And in particular, if one denotes by this binomial coefficient symbol, I mean M1, 2, 3, the space of intertwining operators, then one can exactly use this to get a tensor product decomposition. So in particular, these spaces of intertwining operators, they describe the tensor product of Lie algebras. So for example, for the Lie algebra SL2, these maps or their dimensions, they are usually called Clebsch-Gordon coefficients, or are computed by the Clebsch-Gordon coefficients. So you might have seen that there. And this is the next thing that one wants to do if one wants to chiralize towards the CFT. Now one wants to lift intertwining maps, so that maps that go from that go between different modules. And one wants to do this because this is really what fields in the conformal field theoretic sense will be. So what one does here is, if one formalizes it, one defines this curly bracket Z to be just power series again, but now one allows any complex exponent for Z. Not before we only allowed integral ones. Now one allows complex coefficients, and one can also allow the logarithm of the variable to appear. And so then an intertwining operator is again defined very, very similar to fields as before. Just know that you take a vector in the first module and associate to it a field, but now the coefficients of these fields are not endomorphisms anymore, but they intertwine from M1 between M1 times M2 to M3. So there are homomorphisms from M2 to M3 associated to the element M1. These have to satisfy again the analog of the Lie algebra Jacobi identity. So everything is kind of lifting Lie algebra structure, and it's this formula in many respects extremely similar to the Lie algebra Jacobi identity, except that this formal delta distribution is floating around all the time. So in this sense, is the lifting to define fields mathematically is a careful lifting of Lie algebra data in many respects. Okay. Now, the notion of intertwining operator is the vertex algebraic notion of what is meant by a chiral field in conformal field theory. So this is why we introduced it. And this is quite abstract. You can later look at the slides and maybe see it again. It's probably nice to have seen it at once. And now we see it explicitly for the free boson again. So how do we do this? Now we have our free boson field capital X, and now we want to take an antiderivative of it. So I denote it here by lowercase x, and I immediately split it into three parts: a negative part, a positive part, and a zero mode part. And they are given by this formula. And this formula, if one does the computation carefully and takes the derivative with respect to z, right? But what does it mean? Then if, for example, z to the n is replaced by n times z to the n minus 1, so the n in numerator and denominator cancel, the exponent is decreased by 1, and if one looks at it carefully enough, indeed, the derivative of this expression exactly gives the free boson field X. And this splitting in three parts is done for convenience, which we'll see in the next slide. But first of all, now one can simply compute again the OPE of this antiderivative with itself, and one gets a logarithm, which makes sense, right? Because if I take the derivative with respect to z and w of the left-hand side, then I, of course, have to do the same thing on the right-hand side, but then I get the OPE of the free boson field capital X, which was of the type 1 over z minus w squared, which is exactly the derivative with respect to z and w of the logarithm. Right? Okay, and why do you introduce this field? Well, you want to use it to build chiralizations of the eigenfunctions e to the nx, or e to the lambda x, let's call it. Okay. Somehow it's jumped. So right, so we would like to define the vertex algebra analog of the function e to the nx as the field e to the n, or here I call the n lambda, so e to the lambda x, but now x being a function of our variable z. And you always know, you know if creation operators are to the right of annihilation operators, then divergences will arise. So if you do that too naively, then you have problems. And so that means you define e to the lambda x in a normally ordered way. And this normally ordered way, if one looks back the slide, one will notice that the rightmost field only contains annihilation operators. So so that it is an and you know the normally ordering rule is whatever annihilates should be to the right of what creates. That has the best chances to get quantities that are not divergent. So this is the canonical way to lift e to the lambda x in the sense that it puts everything that annihilates the vacuum to the right. Okay, and now one can compute what it satisfies. And for example, it satisfies the OPE with a free boson field that this field appears, but now with multiplicity lambda as a first order pole. Hope the slides somehow disappeared, right? Or are they still there?
I can see it.
Hmm? You can see them?
The
They-
pointer, you mean?
no, my slides, they disappeared on my
No, I can see it. I can see your
oh, okay,
slide.
now they are back. Something is yeah, they just now they are back as well. Okay, good. So what did we have? We had the derivative d dx, which acts on the function e to the lambda x by multiplication with lambda. And you see, this is again a perfectly chiralized version of it. d dx chiralizes to the field x of z. The function chiralizes to this field curly y of lambda. And instead of having the field acting by multiplication with lambda, we also get a 1 over z minus w in addition. And moreover, one can also compute the OPE of two such fields now. And if one does this, one observes that the OPE of the field associated to lambda times the field associated to mu gives us the field associated to lambda plus mu, but now only as a leading term. So there are dot dot dots means sub-leading terms, and the coefficient is a z minus w to the lambda mu. But again, it is a natural chiralization of the statement that the product of the function e to the lambda x times e to the lambda mu is the function e to the lambda plus mu x. Right? Just but we observe something. If lambda times mu is not an integer, then if I swap the order, right, I have a w minus lambda and w minus z, then the swapping the order of the two fields changes the expression by a phase, by an e to the 2 pi I, e to the pi I lambda times mu. And that's a problem, right? Because what does one want? One always wants single-valued functions. One doesn't like these monodromies, because then that means simply that the field is not well defined on my Riemann surface. So this is here the problem, but also we are simply starting to construct the conformal field theory. We do it step by step. Yeah, I come to the next step in the next slide here. I also want to illustrate something that you probably have seen. Right? Once one has constructed fields, one wants to use them to get correlation functions. And in particular, if we denote by this symbol here the dual of the vacuum, then we can use it to compute correlation functions. And for these fields of the free boson, they have the very nice form that they are just given by this product. So it's a certain meromorphic functions. But we see again, if lambda I times lambda j is not an integer, then we have monodromy. These functions are not single valued in that case. Okay, so we have to avoid this. So so far, our analogy is that I said this many times, so I'm repetitive of course I should be. So the free boson field x of z chiralizes the differential operator d dx, and the intertwining operator, this field curly y of lambda and z, chiralizes the function e to the lambda x. Now, the free boson chiralizes functions on the real line, or if you don't like it and you prefer compact manifolds, we can also think about it as the free boson on the unit circle. And the problem is here, we are dealing with an Lie group, but an abelian one. And abelian Lie groups are a little bit too simple to so that they are sometimes hiding interesting structure. And Lie groups actually have two actions of an underlying Lie algebra, where we are left invariant vector fields and we are right invariant vector fields. Just if the Lie group is abelian, the two actions coincide, maybe up to a sign. So this is why we don't see them. But what the conformal field theory wants to do is it wants to parallelize the functions on the suitable space, and it wants to parallelize the left invariant vector fields and the right invariant vector fields. So it wants to keep two Lie algebra actions, and so that means we want to have a chiral algebra and an anti-chiral algebra acting as a symmetry algebra on the space of states of the conformal field theory. So this means we are actually looking for two copies of the vertex algebra. Right? The vertex algebra was just the mathematician's synonym for symmetry algebra. And the point is now we want to take these two copies and glue now functions for these two copies in such a way that we get nice single-valued operator product algebras or correlation functions. And I already gave you quite a few definitions, right? I defined vertex algebra, I defined a module and intertwining operator, and you saw all these definitions are tedious, and I only gave those for illustration purpose so that you see these things can be made rigorously, and no one can also make the notion of a conformal field theory, at least at genus 0, rigorous. It carries the name full vertex algebra. Would be 2-3 slides, and they wouldn't be too instructive. All I will do now is I will simply I will continue by describing the free boson in the spirit as before. So what we do is, so Lie theory tells us I need two actions of differential operators, a left action and a right action. So that means I define now two copies of a vertex algebra of a free boson. I already defined the field x of z, and now I define a second field which I call x bar of z bar, where I think about z bar as the complex conjugate of the variable z. And I require everything to be the same. This means the OPE of the antichiral free boson field is as before, just that a bar is put everywhere. And on the level of the algebra of modes, simply the barred quantities commute with all unbarred ones and otherwise satisfy the same relations as the unbarred ones. But one does one thing, one identifies the zero modes. The zero modes anyway commute. And we simply don't want two zero modes to be floating around. And in some sense, this identification of the zero modes is actually the gluing condition that ensures single valuedness of operator product algebras and correlation functions. And now for this barred vertex algebra, the antichiral one, everything is defined in exactly the same way as before, just that z is replaced everywhere by z bar, and that's it. And of course, and x by x bar, and xn by xn bar. Okay, and in particular, we also define as before an antiderivative of the free boson field, and the formulas are exactly the same as before, just that there's a bar put before. And then once one has defined the antiderivative, one can define its normally ordered version of its exponential, which is the good field for the free boson vertex algebra. And so here this slide is nothing but a repetition, putting bars everywhere. Okay, and now we don't want the clumsy notation, the field corresponding to the vector lambda and z times the field corresponding to the vector lambda bar and the z bar. So we just call it the field phi with a label z, lambda of z and z bar. Okay. And now the genus zero conformal field theory has as a space of state the direct sum of Fock modules f lambda times f bar lambda, so the chiral Fock module times the antichiral Fock module, and the sum is over any additive subgroup of the complex numbers. But usually, so for example, if you want to think about it compactified, you take the integers, but it's and uncompactified the real numbers. And then you would also replace the direct sum and direct integral. That's not so important. All you see, it's nothing but the sum is a nice diagonal gluing of Fock modules. And now one can compute the OPE, and the OPE of the chiral field associated to lambda with the chiral field associated to mu gives us a z minus w to the lambda times mu times the chiral field associated to lambda plus mu. And for the antichiral one, the same thing. So that means it's, but now z minus w times z bar minus w is the absolute value squared. And that's, of course, a very nice single-valued quantity. So here, unfortunately, I forgot to write phi lambda plus mu. So here, I have to correct this on the slide. I missed that. Okay. And so here you really should appreciate this formula. The only difference to the previous one, if we go back, is that we have an absolute value sign, but absolute value, of course, the absolute value of any phase is 1, and that has then the effect that this expression is nice and single valued. So that means the operator product algebra is well defined. It doesn't depend on the order of the fields. And if we do this now for the dual of the vacuum, that means we compute correlation functions. We have the same effect, while on the chiral side we had for correlation functions. This is just the difference of the insertion points to the lambda I times lambda j. Now, because we did our nice gluing, we have the absolute value squared of these quantities. This means expressions that are nice and single valued. Good. Okay. So what was our idea? This is terminates the first half of my presentation. So the idea is that we are kind of familiar with quantum mechanics. So we choose a space of function and find its algebra of differential operators. We illustrate it in the very nice example where the differential operator is just d dx and the functions are just the eigenfunctions of type e to the nx Fourier modes. And then we chiralize the algebra of differential operators to vertex algebra, to the symmetry algebra of the CFT. Then we chiralize the functions to firstly modules, but then much more important to intertwining operators, because intertwining operators tell us how one function acts on another function, producing a third function. And then the problem that arose is that operator product algebra was not single valued. And the way to fix it is to glue chiral and antichiral parts in such a way that everything becomes single valued. And that is something we wanted anyway, because you know from your course that a conformal field theory has a symmetry algebra that acts via chiral fields and also via antichiral fields. From the quantum mechanical perspective or the classical perspective, the reasoning is that on functions on Lie groups, you have an action of left and right invariant vector fields. You have two copies of the Lie algebra acting. And all this could be said to be a way to define and construct a genus zero conformal field theory. Genus zero because if you go to higher Riemann surfaces, then well, things become very difficult. Okay, so now would be a possibility for a break if you want a break. Okay, welcome back everybody. So I now want to repeat the idea of the first part in a second example. So the idea is that we have a certain principle, that we have our somehow classical or quantum mechanical problem, and we lift it. So this means we choose, first of all, what we want to study. That means we choose a space of function, we find its algebra of differential operators, and then we lift. We call this lifting procedure chiralizing. So this means we lift the algebra to a vertex algebra, to the chiral algebra of the conformal field theory. That's maybe why I call it chiralizing, because it gives the chiral algebra of the conformal field theory. The differential operators, they act on functions. Functions are lifted to fields, and these fields we call intertwining operators because they formalize what a classical intertwining operator, for example, of modules for a Lie algebra is. Now, the problem that we had is that if we just do it this way, we get operator product algebras and correlation functions that are not single valued. But if we then take a second copy of the symmetry algebra, the antichiral algebra, that means everything depends on a barred quantity, a complex conjugate one, then then gluing it in an appropriate way gives us single valued fields, so correlation functions and operator product algebras that only depend on absolute value of difference of insertion points. Okay, and now what we want to do is we want to do this once more in the remaining lecture, and we want to do this for an example of a logarithmic conformal field theory. So logarithmic conformal field theory, you'll have their name because logarithms appear in OPE algebra and in correlation functions. So that's then a well-deserved name. And it turns out they are quite complicated. Actually, not much is understood in general. And they have one, very much like the normal conformal field theory, the rational one, or whatever we want to call it, has a nice basic example with a free boson. The logarithmic ones have a nice basic example, the symplectic fermions. So fermions, it means it's a super CFT. Symplectic fermions, don't confuse them with free fermions. Free fermions are much, much better behaved than symplectic fermions. So there's somehow a big difference in the quality of the problem. Okay, we want to chiralize a classical problem. And so now we first choose our functions. Our functions, we just take the algebra of functions in odd variables. So we want to get something super. So maybe the best way to do it is just take polynomials in two odd variables. We need two because otherwise we will never have a notion of a sensible pairing. That's the problem. So odd variable just means that they anti-commute. In particular, this equal means a plus. It means each of them squares to 0, and the anti-commutator of them is equal to 0. So in particular, it means polynomial odd variables is a very small vector space, just a 4-dimensional. It has the constant polynomial, the linear ones, and the quadratic ones, and nothing else. Yeah, because and the square of any of the odd variables vanishes. Okay, and on these functions we have also differential operators acting. Differential operators have the same rule, right? Derivative of theta plus with respect to theta plus is 1, and similar for minus. With the only additional rule, they are also considered to be odd, so they also anti-commute. Okay, and you already see from the setup that it is extremely similar to even differential operators. The only difference is it's odd. And now we will study what's the difference if we do something odd. Okay, now, well, we chiralize as before, and right, but so this means we would now want to introduce fields that correspond to our differential operators. So the field corresponding to the derivative with respect to theta plus, we denote by chi plus, with respect to theta minus by chi minus, and the form is very similar. The field is sum over the integers, certain modes, times z to the minus n minus 1, and the OPE algebra of the corresponding fields is very similar to the free boson OPE. Just know that we say that the field chi plus of Z has non-vanishing OPE with the field chi minus, so that it has an off-diagonal pairing, and because the pairing has to be antisymmetric, you simply need a partner to have a non-vanishing OPE. So you can't have just a single symplectic fermion. Yeah, and these fields are called symplectic fermion, and they're called symplectic exactly because they always come in pairs, and so they, in particular, the pairing defines a symplectic form. Now, this OPE algebra translates to the commutation relations of modes, and again, they are enormously similar to the free boson commutation relations. So there, nothing new is happening. Okay, now, but we now want to proceed as before. So, and now we can be quicker because I don't have to recall. I mean, on the vertex algebra side, that means on the chiral algebra side, all is the same as before. We have this algebra of modes. We can define a vacuum module in the same way as before, as having a vacuum vector on which all positive modes act as 0 and negative ones create the whole space. And where we want to go to is to the full conformal field theory. So this means we immediately add a second copy of the symplectic fermions. This means we have two sets of modes, chi plus minus n, and the barred ones corresponding to the complex conjugate. But we do also the same thing as before. We identify the barred and unbarred zero modes. So this all what this says is we take all the barred and unbarred modes, and then but we don't want to have two sets of zero modes, and also here the zero mode, the zero label is missing. Now, this one actually admits a bigger central extension, and that means we add just the constant 1 and the theta plus minus our coordinates on that define the algebra of functions, and we use these coordinates to actually also get non-trivial commutation relations with the symplectic fermion zero modes. And this makes sense because what you want to do is you want to identify the zero modes of the symplectic fermions with the derivatives with respect to theta plus and minus. And of course, the derivatives have the property that they have a non-trivial commutator or anti-commutator with the coordinates. So anyway, what one needs to know is simply the big, let's say, big algebra of modes and their commutation relations, which is given by these formulas. Okay, and now we want to lift this, and now we do this in one go. So what do we do is we want to define a space of states, states of the conformal field theory. So we take a vacuum on which all positive modes act as 0, and we let everything else act freely, also the theta plus and minus. And so this means it's this big polynomial ring. And what I did here in the second line, I split it into two parts. Because the way to think about it is you take your algebra of functions, which are just the polynomials in theta plus and minus, and then let's simply create from there the whole space of states of the conformal field theory via action of all the negative modes. Okay, so the vacuum satisfies the usual condition that I said before, that it is annihilated by all annihilation operators. That means by all positive modes, including the chi plus minus 0 modes. Okay, now this symplectic fermion Hilbert space turns out to have two conformal vectors, which actually correspond to so it's a super algebra, and you probably have learned that Westomin-Witten models always allow a Virasoro structure via the Sugawara construction, and there's a similar one for super algebras, and it gives this one, but one could also compute it explicitly. Okay. Now, this diagram is kind of important. So what did we do here? We started with a four-dimensional algebra that which is just the algebra of functions in two, or in the polynomial algebra in two odd variables. So we just have the monomials is 1 theta minus theta plus and theta minus times theta plus. And on those, the differential operators dd theta plus and dd theta minus act. For example, dd theta plus maps theta plus times theta minus to theta minus, and dd theta minus maps theta minus to 1. And so these differential operators are identified with the zero modes of the symplectic fermions. So dd theta plus is identified with chi0 minus and vice versa. It's just a convention. And so that means this diagram, which in fact is called the Löwy diagram, if you want, illustrates nicely how the differential operator act non-semi-simply on this four-dimensional algebra, meaning the differential operators only act downwards. They map the degree 2 polynomials to degree 1 ones and degree 1 ones to constant ones, and they annihilate any constant one. But what I put here in addition in the illustration is also the action of the Virasoro zero mode. The Virasoro zero mode, what does it do? It gives conformal weight, right? And but here it turns out that the action of L0 is non-diagonalizable. So we have Jordan blocks, and in particular on this four-dimensional top level, this top level has generalized conformal weight 0, but this is a non-semi-simple part of the action. And this non-semi-simple action, these Jordan blocks of that the conformal weight is generalized to generalized conformal weight. That means one has Jordan blocks, is in fact the reason for having logarithmic singularities in the correlation functions. So here one simply can compute this relatively explicitly. One can also ask what's the action of L naught bar of the Virasoro zero mode corresponding to the antichiral one, and it will also map this top level to the bottom. In particular, it means the difference of the two will nicely act semi-simply. Yeah. So in any case, it turns out symplectic fermions admit a non-semi-simple a Jordan block action of the Virasoro algebra, and from a structural point of view, this is very important. Okay, now here I thought I'd also give some more detailed formula. Now one wants of course to every vector define a field, And so to the vacuum, just the vacuum is always identified with the identity. That's easy. Now the field corresponding to the functions theta plus and theta minus are these expressions. Well, precise formula is not that terribly important, but what is important is here you also see a logarithm, which you usually don't have in fields. And then these fields corresponding to the modes minus m are then appropriate derivatives of the fields theta plus and theta minus. And one can write down closed formulas. And, precise form is not so important. What's maybe important is that while the field corresponding to these functions contains the logarithm, the fields corresponding to these derivatives become much simpler. In fact, you see the fields corresponding to chi plus minus will actually be a chiral field, and similarly to chi plus minus bar an antichiral. That's a feature. That's because the symplectic fermions are nonetheless quite as simple in formal field theory. Okay. And now with this explicit form and the commutation relations of the modes here, one can now compute OPEs and correlation functions and see what's happening. But one can already guess, because a logarithm appearing here, we will actually see logarithms appearing. But before doing so, one has to define a normal ordering, and this you can do kind of ad hoc to us by defining a degree to every mode. And this is just to say that you have to simply say if the mode index is the same, which of them you write to the left and which one of them to the right. And it actually doesn't matter, you just have to make a choice. And then you define the normally ordered product in the absolute usual way, that you'd simply move modes that are more positive to the right of the modes that are more negative. And all you have to include here now carefully is also a minus sign that depends on your permutation, because we are dealing with a super conformal field theory. So that means if you swap an order, then you always have to add a minus sign. And then according to this description, we define fields as a normally ordered product of fields. Okay, and with this prescription, then first of all, just because the fields are expressed as power series in z, w, z bar, w bar, and the inverses and the logarithms, it's clear that any two-point function is, of course, such a power series. And so in particular, what you'll have is a nice locality property. If you swap the order of insertion points, you will get the same expression, except if both of them are odd, then you'll get an additional minus sign. But what is interesting is what the concrete form of the correlation functions is. And that concrete form one gets if one does once a computation, so which I here now wrote completely down. So you want to compute what is the product of two generating fields, and the best way to do it is it is equal to the normally ordered product plus something. So here I wrote down the product of the two field minus the normally ordered product, and that should give us something interesting. And so by the definition of the normally ordered product, this difference is a certain, I mean, as long as you don't reorder the modes, it's just the same expression minus itself, so it gives a 0. But whenever you reordered it, then on the right-hand side, you get an appropriate commutator. So this is, and if you write it carefully down, you get exactly this expression of commutators commutators. But all these commutators, you know exactly what they are, right? And for example, the commutator of chi plus n with chi minus m gives us an n times delta n plus m, comma 0. And you see that's nice because then n in numerator and the denominator cancel. The m is equal to minus n. And so then these sums become quite nice. So now this is always going back. So this means the first line here is simply, I don't know why, somehow it's always jumping here. So the first line is simply carefully writing down what the difference between product and normally ordered product is. The next line is inserting explicitly the commutators. Then the next line is setting m equal to minus n. And then you see this gives m is equal to minus n. So this z to the minus n w to the minus m becomes a nice w over z to the n. The n's in numerator and denominator cancel. The m is a minus n, giving the swap in signs here. And in any case, one gets these infinite sums. And then addition also plus minus the logarithm of absolute value of z. But what are these infinite sums? The best way to see what they are is taking the derivative with respect to, well, w over z actually of this one. Because what happens if I take the derivative? Then then I get an n times this number to this expression to the n minus 1. So n in numerator and denominator cancel. So what do I get? I get a nice geometric series. Geometric series, right? Sum over positive integers x to the n is the expansion of 1 over 1 minus x, where x is smaller than 1. So this expression is an antiderivative of this. Right? Antiderivative of 1 over 1 minus x is the logarithm of 1 minus x. So in this way you can see well, the point is this expression is nothing but the expansion of the logarithm here of 1 minus w over z in the domain where w over z is less than 1, which we require here. And similar for the Barth quantities in this one. And now we think about the rules of logarithm, and they say the sum of logarithms is the logarithm of the products, so that the sum of these three expressions becomes logarithm of well, logarithm of z minus w absolute value squared, right? So in particular, you see the very nice interplay and right, a computation which you have to put in the definitions, which you have to trust me I did correctly, and at the end what you get is a sum of three expressions, each a logarithm, but each logarithm of either only depending on the chiral, on the w and z, or the antichiral, the complex conjugate variables, and then here this absolute value squared one. But they combine nicely in just the logarithm of the absolute value of the difference squared, which is what one wants. One wants at least, right? We always want expressions that only depend on the absolute value of the difference of the insertion points. And now with this computation, one can now take a correlation function where one inserts many of these fields, plus and minus, same number of fields, and now use this rule step by step. And if one does the combinatorics correctly, one sees, well, when one gets one expression for every permutation, or permutation of the number of insertion points of 1/2 the number of insertion points other, assigned just because every permutation produced, because of the oddness, the super part, every swapping of order produces a minus sign, and then you get a logarithm for every kind of point, for every contraction. In some sense, this is nothing but a Wick's theorem for symplectic fermions. Anyway, the important point is, of course, the form of the expression. And what's the difference to the free boson? Well, the free boson was a product of the differences of insertion points to certain powers dependent on the weight of the Fock modules. And here we get logarithms. And hence justifying the name logarithmic conformal field theory. So here what you see very nicely is that the space of states of the symplectic fermion conformal field theory, you can build in complete analogy to the free boson, and there was nothing more difficult here, but the outcome was kind of interesting in the sense that these logarithms appear, and these logarithms are intimately tied to the non-semi-simplicity of the Virasoro zero mode, that the Virasoro mode maps one vector to a different vector. It does not act diagonally. Right, so we have this observation. Logarithms appear. Okay. And as you saw, I decided to present two examples that maybe illustrate. And now let me just quickly mention a few generalities. So we call a representation completely reducible if it can be written as a direct sum of irreducible modules, of simple modules. This is something that you are used to. And that a representation that has not this property is called non-reducible. And in particular, if we have a representation that cannot be further decomposed, it cannot be written as a direct sum of two representations, but is not simple, is called reducible but indecomposable. And the difference, there are somehow two types of conformal field theories, at least naively, so which you should call rational conformal field theory and logarithmic ones. In the rational conformal field theory, everything is completely reducible. The space of states is a nice direct sum of modules. And in the logarithmic case, this is not the case anymore. You might have some representations that are completely reducible, but not all will be. Okay. And one thing about these logarithmic theories is that in particular this non-complete reducibility arises already for the Virasoro algebra. So much can already be detected from the Virasoro algebra. Now, I imagine that you have seen a few examples of rational conformal field theories, for example, compactified bosons, the Virasoro minimal models, and Wess-Suminer-Witten theories at positive integer level. So maybe you have seen the SL2 or SU2 Wess-Suminer-Witten model, for example. And if you look at the literature, or if you think about applications, the early literature, so let's say the first 30 years of conformal field theory, or 20 years, were almost exclusively about rational conformal field theories. In particular, they were enormously used in string theory. Well, that area probably still has open problems. I mean, it has. But usually people say that this is fairly well under control. So one could say it is a subject that has a good and well-established theory. Now, it turns out logarithmic conformal field theories are known for a long time, because but they haven't been studied much, and that was not because of a lack of interest. It was more, they can't be treated in the same way as rational ones. And of course, as a first try, you simply if you have some structure and you know how analyzing a similar structure works, maybe you do it in the same way. But that led to simply to nonsense. And for example, I think it's even in the yellow CFT book, they call logarithmic CFTs, or better, certain logarithmic CFTs, either physically sick or intrinsically sick, one of the two ones. But that's more to a misconception on how to treat this. And over the last decade, there had been really a lot of active research on this, in particular from the vertex algebra community. And it's definitely fair to say that they are not sick. One just has to carefully know what the difference is to the rational ones. Nonetheless, there are only a small number of understood theories. The best understood one is the one that I sketched, the symplectic fermions. There's a family that is quite similar called singlet and triplet theories. What they really are is they are logarithmic analogs of the Virasoro minimal models. They are, in many ways, one could call them extensions of the Virasoro minimal models of type 1, p. It is only the Virasoro minimal models are labeled by two positive integers starting at 2. And so the 1 kind of has the effect to make it logarithmic. Westomin-Witten theories can be defined for supergroups equally well as for Lie groups. And the simplest supergroup is GL1/1, so that's well understood. And Westomin-Witten theories in the rational sense are associated to positive integer levels. If you replace positive integer by rational numbers that are not too negative, then they are called fraction level Westomin-Witten theories. And it turns out only for SL2 that's understood. And that was enormously difficult, and I would not be able to put this into a 2-hour lecture, maybe in a 6-hour lecture, or 8-hour. But this is substantially harder than the symplectic fermions, and you would be surprised what it looks like. From an application, I don't, probably, of course, in your lecturer will surely tell you a lot about also applications. So the logarithmic CFTs, they have had a lot of benefit for the mathematicians. Or let's say it's a nice interplay. What I do know and what has been a lot of fun is that over the last 10 years, one has been able to relate higher dimensional quantum field theories, usually some super Young-Mills theories, to two-dimensional theories. And two-dimensional means conformal, or chiral conformal, that means vertex algebra. And it turns out if you start with the higher dimensional unitary ones, the 2D theory has to be non-unitary, and non-unitary kind of often usually wants to be then also logarithmic. So in particular, there has been really a nice interplay between these types of things and correspondences to higher dimensional theories. Good. This is what I wanted to tell you. Please ask questions.